Let's review. Newton's law of gravity states that the gravitational attraction between any two objects is directly proportional to the product of the objects' masses and inversely proportional to the square of the distance between their centers of mass. Later, Henry Cavendish determined the value of the universal gravitational constant g to be 6.67 times 10 to the negative 11th Newton meter squared per kilogram squared, which turned Newton's proportionality into an equality. That equation in yellow we call Newton's law of gravity. Earth has a mass of 5.97 times 10 to the 24th kilograms and a radius of 6.38 times 10 to the 6th meters. Find the force of gravity on a 34 kilogram rock. In our picture here, we've got a model of the Earth, and this object here is our 34 kilogram rock. We're going to assume it's at the surface of the Earth, and clearly this picture is not drawn to scale. Let's go ahead and write down Newton's law of gravity. I'm going to go ahead and make one of the masses the mass of the Earth, and I'm going to make the other mass the mass of the rock. So let's see if we've got these numbers correct here. G is 6.67 times 10 to the negative 11th. The mass of the Earth is given right there in kilograms. Notice that I've left the units off of this equation, but I've only done that because I checked them at the beginning and I know they're right. The masses are in kilograms, the distance is in meters, so to save space in the writing out of all this, I've left the units off, but you definitely need to check them before you do the work on your problem. There's the universal gravitational constant, there is the mass of the Earth, there's the mass of the rock, and the distance between the centers of mass of those objects is essentially the radius of the Earth. Notice that we've squared that radius. That takes a little work, but if we type that into our calculator, we get 333 newtons. That is the weight of the object. And for a long time now, we have calculated weight by taking the mass of the object times little g, which on the Earth is about 9.81 meters per second squared. Well, look at that. 333 newtons. Which means, up here, we should be able to set this Newton's law of gravity equal to the mass times little g. Now this mass is the mass of the rock. So what we have here is the mass of the rock times little g is equal to big G times the mass of the Earth times the mass of the rock divided by the radius of the Earth squared. I think I should be able to cancel the mass of the rock like that, which means look what we have. There's little g all by itself, and there's an expression that we can use to calculate little g. There you go. That's how we could calculate little g for the Earth. We're going to take the gravitational constant g times the mass of the Earth divided by the radius of the Earth squared. We'll get about 9.81. We could use this same expression to find the acceleration due to gravity on the Moon, or on Mars, or on Venus. We simply have to put in this equation, along with the gravitational constant, the mass of those planetary bodies and the mean radius of those planetary bodies. That's pretty neat. If a 12 kilogram rover weighs 44.5 newtons on Mars, find the mass of Mars. There is our 12 kilogram rover. Let's see what we've got here. We know the radius of Mars. We know the mass of rover. We know the force of gravity between them. That is the weight of rover, 44.5 newtons. And of course, we know the Cavendish constant, or the universal gravitational constant, so we should be able to calculate the mass of Mars. Let's multiply both sides by the radius of Mars squared, and then divide both sides by g and the mass of rover, and that gives us the mass of Mars. So all I've done here is solve this equation for the mass of Mars. Now we're going to put our numbers in. There's the force of gravity, which is the weight of rover. There's the radius of Mars, the gravitational constant, and there's the mass of rover. If you type that in correctly, you get that number, 6.43 times 10 to the 23rd kilograms. What's G on Mars? Well, there are any number of ways you could find this, but we're going to use the equation that we introduced on the last slide. Now that we know the mass of Mars to be right here, 6.43 times 10 to the 23rd kilograms, there's the gravitational constant, there's the radius of Mars squared, 3.71 meters per second squared.